It's okay. They should have come to class, right? Yes, exactly. Especially because today you are here. So your 15 volt minus 15 volt, what's going to be the potential between the 2 points? 30 volt, very good. So you remember you have an outlet here from those machine, the laundry machine, the washing machine, the microwave, the AC unit, and you have two hot lines. So one is at minus 120, so it's like a dip, minus 120 below the ground. One is at 120 above the ground. So what's going to be the difference in voltage? 240 volts. So that way we can give them more energy for the same current. Will be more energy available. Okay, so a lot of applications. So of course the heart is an electrical system and you do have potential difference. So for example, here you're going to have a hill, so it's positive potential. Here you have a negative potential relative to the ground. So you can find the potential between them. That's what you do with a EKG. You are finding potential difference between 2 points. And I'm sure you know how to read that. I don't know how to read that, but one is normal and the other one is not normal. So these are equipotential. So that will be for a dipole. You see, negative here potential, positive potential. You can have interesting configuration. You can have a plus here, plus here, plus here, minus there. You can trace the equipotential. And you see that the electric field is always showing you the way, okay, for the potential to decrease the faster, okay, go this way. So it's very much like a mountain or a hill. The water will go down the steepest slope. So kind of the same way, same thing. Okay, another interesting thing is that if you have something with a curve, okay, so here you have it's like a pointy here. So if you have the curve is sharp. You have a sharp turn here. Sharp turn means you're gonna have more charges accumulating, so you're gonna have a stronger electric field. If you have a stronger electric field, you increase the probability of a discharge. So that's called coronal discharge. So each time the curvature here is small, okay, it will have a larger density of charge. So the electric field will be very, very strong. Okay? And if the electric field is too strong, that means it's going to pull on those charges like crazy, then what's going to happen? You're going to ionize the air around. Okay, you're going to have a spark. So, for example, if you walk, I don't know, I went to Key West. I don't know what's the problem with their electric system, but if you go under those high tension line, you hear this noise non-stop because it's discharging non-stop. I don't know what the engineers are doing over there. Maybe they are all on the beach or scuba diving, but this is. I'm not sick. Okay, it's just the dust. It's very dusty. I don't know if it's the dust or the chemicals. So anyway, when that happens, you are losing money. Not you, not the consumer, but the electric company. Because you see, you have a discharge. And you can even smell it. Because when you have a discharge like this, that means you're going to have the air is going to be ionized and oxygen will turn into O O3. O3 is called ozone. Ozone. You smell it. It has a very weird smell. O3 is ozone. So I think we talk about that, no? That happened in the before World War II during Nazi Germany, and so in Berlin, they had this blimp here, and it was doing the journey from Berlin to New Jersey. So it was during the Nazis, and what happened? This called Hindenburg disaster. What happened? It caught fire and everyone died inside. And they thought it was like a terrorist attack, but it was not. You know what happened? What happened here? You see, this is a pole connected to the ground. Here inside you have helium, and you all know that helium is very inflammable, right? It can catch fire. And here you have a lot of rubbing happening on the outside of the balloon. So a lot of charge accumulating. Okay, so if this is plus, all the minus from the ground is going to rush here, over there. You're going to have an electric field between plus and minus. And this electric field is going to be so strong because it's pointy here. You have a point here. So strong that you're going to have a breakdown. The air is going to be ionized. Electricity is going to flow. And of course, it's going to catch fire. So after that, they stopped. They stopped making those balloon. It was good because helium is very light. Okay, so it's very efficient, but it's also very dangerous. I think we talk about that. All the nervous system is an electrical system, and the signal, the way it's propagating, you have a propagation. It's not charges moving, but it's a voltage. Okay, so this is rest, and then you have those ions moving in. So that becomes minus, that becomes plus. This is the inside of the cell, and it switches back and forth, and that's how it's moving. So this is called action potential. And if you are interested, since most of you are in biology, yeah, I found this very nice website. You see how it's connected to the brain. Okay, all those cells that make up the nervous system, they are made of neurons, and you see how they have a layer here. This layer has a very large resistance, so the signal cannot leak out. Otherwise, there is, I'm sure you know, it's called, I don't know what it's called, but there is an immune disease when you don't have enough layer, so the signal leak out. Do you know the name? I forgot the name. What's the disease when you don't have enough layer here? This is called myelin that goes around the neuron. And if that layer it does not protect, it's not insulating enough, so the signal can leak out. And it's a maybe yes. Okay, and you have no, not cancer. Cancer is another issue. Eh, yes, yes, say it out loud because I cannot say it. Say it out loud. Multiple sclerosis. Hi, that one. Multiple sclerosis. She said it. And that's why, by the way, this here protective layer myelin is made of cholesterol fat. So that's why we need fat. We need animal fat. Okay. Okay. Let's move to the next unit, capacitor. By the way, we do have like a test coming, number 2 after spring break, I think. No, I have problem to do. How come I don't see my problem? I went too fast. That's it. I didn't have problems. No. Any question on that unit? Is that clear? Make sure you read your textbook, okay? You need something to read so you can digest it better. So let's talk about capacitors, okay? Still attached to the same unit. The best example I can think of is a defibrillator. So how does it work? A capacitor or a defibrillator in that case, it's made of two conductors. Two conductors, right? So you have two conductors like this. This is connected to a power supply, okay? So you're going to charge the capacitor to 100 volt to about 1000 volt, 200 to 1000 volt. It depends what you need to do. Is that just to resuscitate someone who is almost dead, or is it just to give a little boost in your heart? So it depends on that. Okay, so it's going to be charged. So one will be positively charged and one will be negatively charged. So it's like a dipole. Between them, you're going to have an insulator. So you see, you have one positive, the other one negative. Before you place it on the body, between them, you're going to have the air. The air is an insulator, right? And there will be a voltage between them. And they are equipotential. So that will be, for example, like 100 volt. That could be at zero, so 100 volt relative to zero. In between them, you're going to have an electric field. And then you place that, so you charge your capacitors, you charge your defibrillator, you place it across the heart, and this is, of course, a conductor. So it's like the tissue here is like your connecting wire. Your heart is like your load, like a resistance, right? And you're going to discharge it in your heart. So all the energy that was stored inside your electric field is going to be discharged in your heart. And you're going to have a huge surge in current going through your heart. You can also add a resistance if you want to control the amount of current per unit time. Okay, so you're going to have a huge surge of current going through your heart, and the idea is to have the heart start to go again at a constant rate, or to make it start beat again. That's the idea of a defibrillator, and that's how it's an example for a capacitor. Is that clear? So I already show you. I have another very nice app. It's fantastic, fantastic tool here. So you see, you have a voltage that could be the two parts, the two components of your defibrillator. So you're going to increase the voltage here. Okay, so that plate will be at 1.5 volt relative to the other plate. You see, you accumulate the charges. Is that clear? Right? In between them, you're going to have an electric field. How can I change the amount of charges here? If I increase the area, what's going to happen? Increase, very good, because you have more space, right? It's like you have a building and you add one more floor, so you have more space for the charge to flow and come. If we decrease the area, the amount of charge is decreasing. So for a parallel plate capacitor, and it depends on the geometry. So if it's parallel, okay, it depends on the area. So it's proportional to the area. Now, what's going to happen if I change the distance between the plates? So it's kind of counterintuitive, but not so much. Like if you decrease the area, look what's happening. Not decrease. If you decrease the distance between the plates, what's happening to the number of charge? Increasing. Why? It's like you are increasing the motivation. It's like the plus, they can see the minus, they almost can't touch them. So they are very motivated, right? So you increase the charge. If you increase the distance, you decrease the charge. Okay? So very soon, I'll show you, we're going to define a new physical quantity named the capacitance. Capacitance is like capacity, so it means how much charge it can store per unit volt. So look at the capacitance here. If you increase the area, you change the geometry and the capacitance is going to increase. You see that? If you decrease the distance, what's going to happen? Increase. So it's like a small beaker or big beaker, right? You change the capacity. And then you disconnect it here. Is it holding the charge? Is the charge going anywhere or they stay there? They can stay there for a very long time unless the air is humid. If it's too humid, it can leak out. That means that even though you disconnect the defibrillator from the power supply, it's fine. You are holding it in your hand and nothing will happen. It's not going to kill you. And then you put that on the heart, across the heart, and you discharge it because it can hold the charge. Now, look at that light bulb. This light bulb could be your heart, could be a light bulb. It will be the load. What's going to happen if I connect to it? You have a flash. That's how, the portable camera work. Okay, you have a capacitor that will burp out its energy into a plasma tube. And you have a flash. You can control how long the flash is going to last by increasing the resistance. Okay, so I have a demo to show you. So you have here. So this is a capacitor, and it's just for demonstration. But can you read the number here? What does it say here? One watt. F is the unit for capacitance is farad. It's named after Faraday. Okay, we're gonna see that capacitance means the coulomb per voltage. How many coulombs I can store for 1 volt? So here I can store 1 coulomb per volt. This is just for demonstration because 1 farad is huge. What's the voltage here? 5 volts. So it means you should not try to charge it with a voltage larger than 5 volts. Okay, so I'm gonna, here I have a power supply. I made my own power supply. And I think it's 4.5. That's my power supply, okay? Do you see that or no? Can you see the number? Can you see? It's like 4 points. Oh, here you go. 4.6 volts, okay? So I'm gonna charge. I forgot which way to do it. I think it's polarized. So I'm gonna charge the capacitor. Okay, so it's gonna charge. Sometimes it takes, do you see how the voltage is gonna increase? 1.4. Do you see how it's changing? 1.7, it's about 2. 3, 4, 5.8, 5.6. Do you see that? So this is called charging a capacitor. So the voltage is 0 to begin with, and it's going to increase. So first it's going to increase fast, and then it's increasing slowly. So now it's charged. You agree? And now I'm going to disconnect it. I'm disconnecting it. Okay? Do you believe me? Okay, no more power supply. But it's still holding the charge. I should not touch it, otherwise I'm going to discharge it, but it's holding the charge. See, 4.5, it's holding the charge. And now I have a load. Here. And I'm going to connect it without... do you see that? Do you see? So it's not connected to a power supply. I don't need a power supply anymore. I just need my capacitor. So this is called discharge. If it's going very fast, then you get a flash, like in a camera. So in that case, that means the resistance is very small. Because very small resistance means it's like the pipe are very large, so it's going to burp out everything at once. If the resistance is very large, it's going to take more time. And now it's being discharged. Do you understand? Those capacitors are safe, but some capacitors, they are called ultra capacitor. They can be deadly. It can kill you, because if you open a device like the old TV and there is a charge capacitor inside, and it's a large capacitor, ultra capacitor, you touch it, it's going to send a burp of current inside you and it can kill you. So very dangerous stuff. Those little capacitors are not dangerous. Nothing to be afraid of. Oh, I forgot to show you also. Uh, so if you play, with computers, okay, if you are mining or things like that, you see inside the computer, you see all those components. These are capacitors. They are everywhere in electronics. They look like cylinder, and on it you can read the capacitance. Usually here I read 470 microfarad, 25 volt. So any electronics that you're gonna open, you're gonna have those capacitors here all over. You can hack. You can even use X-ray emitter. No, let's forget that. That's too dangerous. I had a video about ultra capacitors. So this video, I forgot to show it to you.
The prudent traveler wants to know.
Let's go back. It's not about capacitor, but it's to draw the parallel between voltage and altitude. So same way, you have to do work against gravity to go to a higher altitude. If you have 1 coulomb of charge, you have to do work to place it at a higher voltage, which is potential energy.
About it, because going uphill can be hard work. And exactly the same is true for electric potential. Moving up the incline of potential is hard work.
go up the potential 4.5
And the steeper it is, the harder it is to climb.
This is the electric field showing you which way to go.
Of course, if the potential isn't changing, it takes no
You see, the plateau is inside your Van Graaf
work at all.
generator. No electric field inside.
And if the potential decreases, the field is downhill all the way. In this analogy, electric potential is elevation, and electric field is the downward slope. To put it in more mathematical terms, the electric field is a negative derivative of the potential. Or, in other words, the potential is minus the integral of the electric field.
So it gets into calculus, but it's fine. What you see here is a point charge. Okay, it's not really a point charge. Let's say it's like a small Van Graaf generator. You see the electric field here away, and you see that the potential is going to decrease as 1 over x. As you move along the x-axis, that will be 1 over x. It's just a way to visualize. I had a great video with ultra capacitor, but it's in your canvas. Okay, here you see you have the electric field, which is uniform, and you are storing energy into it, and it's holding the charge, and all that energy stored inside the electric field can be burnt inside the load. Okay, so this is called charging the capacitor. This is called discharging the capacitor. So even if you have a Van Graaf generator, you can think of that as a capacitor because it's holding charge. So that will be your plus Q. Where is your minus Q? That will be the ground. That will be very far away. So Van Graaf generator is a capacitor, but it's not a parallel plate capacitor. Okay. If you want to get a capacitor, like you can open a portable camera and they have a huge capacitor inside of 3300 microfarad. Okay, so that will be the capacitance. Because all that energy, so you're going to charge your capacitor and it will be discharged into like a flash. Right? It's like a small plasma tube, and all that energy will go into light. So that was a breakthrough in the 1930s at MIT. A professor here developed high-speed photography using a capacitor that will discharge into a plasma tube. It's like a plasma globe, that it's a tube. And that bulb, a plasma bulb, it's called a plasma discharge. So you will have a huge flash during a very small time because the discharge happened very quickly. So then in that case, you could have high-speed photography like this, right? Because it's like a thromboscope. You lit and then it's dark. Flash, dark. Flash, dark. So you can show all the steps here of the motion. So that was a big revolution. It's amazing that you can see that. So it's used a lot and it could be very dangerous.
In this video, we're going to commit random acts of destruction and learn a few things about capacitors along the way. So recently, Electronic Gold Mine had a great deal on some ultracapacitors, and I bought a whole bunch of them. Ultracapacitors are like regular capacitors, except they can hold much more energy. Here's an example. This is a 560 microfarad 200 volt electrolytic capacitor, and it's about as big as you'll ever see on a consumer circuit board. The energy stored in a capacitor is given by this formula. If I apply it to this capacitor, I can see that it can store a maximum of 11.2 joules.
So we're going to see that equation here. Okay, you can find how much energy you can store in joule inside a capacitor. So it depends on the voltage squared, and of course it depends on the capacitance.
In certain circumstances, that's enough to do some serious damage. Now, the ultracapacitors I bought are 2,600 farads, and that's not a mistake, 2,600 farads, with a maximum of 2.5 volts. That means that one of these ultracapacitors can store 8.1 kilojoules of energy, which is a ridiculous difference. So let's see what a few kilojoules can do. Here I have the ultracap charged to 2.35 volts, and you can already see, this thing means business. Let's start out by burning some soldering braid. Now let's melt an inductor.
So what you're doing here, you are discharging.
Here I'm shorting the cap across a 5-cent coin.
Whoa.
So the idea is you can have a huge surge in current being burped out in a very small amount of time.
Wow, that beaver really took a pounding.
I don't think it's legal. Can you do that?
And I thought it was fun to make these PCB traces light up like glow wire.
Yeah, maybe if you don't change the value, then it's fine. Okay, it's in your canvas. You can look, and then I can skip.
But when I tried to charge it up, I ran into a bottleneck. Let the fun begin.
So now
Ooh, this is gonna be
several
good.
Capacitor placed in parallel, so it's even worse. So he's wearing gloves now.
Well, the PCB traces aren't melting anymore, now they just vaporize.
So it's vaporized, so it doesn't melt anymore.
And it turns out that the insulation on magnet wire is flammable. I didn't know that. Let's try it with 10 cents.
Whoa.
Oh.
Looks like this ship has sailed. Finally, let's vaporize a nail.
So you get the point. So what he did here, he took ultra capacitor, so it's like 4,000 farads, and he has them in parallel. So in parallel, that means if you have them in parallel, you're gonna multiply the capacity. So if you have two capacitors, the capacitance will be multiplied by 2. So you increase the capacitance, you charge them. You don't need a high voltage. You can just use 5 volt or 2.5 volt. You have to wait long enough. And inside here, you're going to accumulate a huge amount of charge. So those things can kill capacitors, right? So I'm going to skim through. So I'm going to stop here, but I'm going to skim through this unit so we can start talking about magnetism.